Hello, I'm Peter Clayton from PicoCom, and PicoCom's a semiconductor company. We're developing SoCs for 5G new radio infrastructure.
Hello, I'm Gajinder Panisar. I've recently joined Mentor Test and Embedded Analytics through the acquisition of Ultrasoc. We provide on-chip monitoring infrastructure to help ensure systems are safe, secure, and they do what they were designed to do.
So we're going to start off with a bit of animation to show how PicoCom's products fit into the world. An SoC device here from us. Typically go maybe into a radio unit like this on a wall, and this allows people with 5G, 4G, 5G phones to communicate over the air to that device. Typically that will be connected along with a lot of other devices to somewhere in the building, a central place with a distributed unit to bring together the all of those radio units. And as well as in buildings, PicoCom's products can go into small cell deployments, typically in buildings, in streets. So looking at that in a bit more detail, we can see some slices from that animation. The radio units there on the top left, now they will have all the actual radio electronics in there and a small amount of digital electronics, the minimum that's required, connected typically through fiber connections or maybe 10 gigabit copper Ethernet down to a distributed unit in the building which has a lot more electronics. And it's the chip in its mode of being used in the distributed unit that I'm going to be talking about during the rest of this presentation. We also have within a city or with a part of a city, typically all these buildings and outdoor deployments will be connected back to a central location, which will be the network where the network operator maybe has their core network. So this is a representation of what's in that, the chip that goes in that distributed unit. On the right hand side, we have a PCIe interface, which is connected to the layer 2 and high layer stack processing. This is a PHY layer chip, a layer 1 chip. We have a cluster of Andis RISC-V cores here, which I'll talk about in the next slide. On the other side, we have an Ethernet interface. This uses a protocol called eCPRI over 25 gigabit Ethernet to connect this to radio units throughout a building. Now that also has an identical cluster of Andis RISC-V cores. So also on the chip, we have a DDR interface where the DDR is used for temporary storage of data. A lot of the processing is done by a combination of CEVA RISC-V cores, CEVA XE12 cores. These are big vector processing cores and hardware accelerators. And of course, we have a bucket load of RAM on the chip, and it's all connected together by an Arteris NOC. So looking at a bit more detail at one of those RISC-V clusters, and they are actually both identical apart from the memory configuration along the bottom. Each consists of 20 RISC-V cores, no, 20 RISC-V cores. They consist of 16 RISC-V cores, all connected together in a local NOC, which is connected to the main NOC. Now we opted to have a large number of small cores here, as it goes better with the high-speed processing of header data that we need to do here. I'd also like to point out here at the top left, the Test and Embedded Analytics fabric, which connects into the what's called a process analytics module here, which allows us to monitor and control the processors in this cluster. Well, so what's so hard about 5G baseband processing? Lots of companies put lots of money into doing this. Well, firstly, 5G is actually far more flexible than 4G. If we look at the diagram on the right here, we can see that processing is done in slots, and these slots consist of 14 OFDM symbols, which contain the data and control channels that are sent over the air. So whereas in 4G a slot was a millisecond long always, the slots can be of variable length, the shortest being 31.25 microseconds. And typically the processing for one slot takes place in the previous slot, and then that slot is, the data for that slot is sent out over the air and going the other way on the uplink. So we're also processing uplink and downlink data at the same time. And there are a large number of different slot structures consisting of uplink symbols, downlink symbols, special symbols. So as well as this, that seemingly quite nice structure of things going through, there are actually unexpected things can happen. One thing in particular is ultra reliable low latency communication, which is one of the three main use cases of 5G. And in URLC, data can arrive at any time and has to be processed. So all the processing that's going on for the slot structure above has to stop and be bypassed. So in addition to this, baseband units in the distributed unit there can be talking to quite a number of radio units at the same time with several antennas. There may be software there from several mobile operators, and in the 5G era, we're moving from an era in a telecoms world where you've got software updates maybe twice a year, so pushing software updates into the field far more frequently than that. So what can possibly go wrong? Well, if we look at the, we actually find that there are a lot of things happening all at the same time, as we were saying in the last slides. Hundreds of users, and everything is dependent upon each other. So looking at this diagram, if, for example, we had some URLC data coming in which pushed out the processing, it will push out the processing for other things in here. It may be a hardware accelerator or more, some of the software processing. So it will make something else late. And if we overlap the slot boundary here, processing will go into the next slot, so data won't be available to go out over the air when it needs to. And this could cause the whole system to fail. In practice, this probably means you lose 2 or 3 symbols, so it's not fatal. But if that happens, it's going to degrade the user experience. So network operators are going to be a bit upset about this happening. So you can find out if this is going wrong in the lab. It's still quite difficult to figure out what's happening here. But in the field, it could actually happen, maybe years after the unit has first been installed, possibly after as a result of a software upgrade. And we can also have several mobile operators using the same base station. Which could mean that software from one mobile operator is upgraded and software from others aren't. So we need something that's actually independent of all the software that's on the device here in order to work out what's going on. So I took this problem to my friend Gadge here and asked how he could help.
Thank you, Peter. You have quite a challenging problem to solve here. I mean, you're going to support hundreds of users at the same time, several operators on the same device. Each of these operators may have their own software running at the same time in the device, coexisting with other operators' software. You have timing constraints that are quite rigid, and you have this other set of channels coming where the timing constraints are even more severe. And then this is on top of the fact that the 5G standard is evolving, and you need to track that and be able to update your baseband software to make sure that you're compliant with the latest releases. And then not forgetting the complexities of the system, the SoC that you have, where you have many cores and interconnects and shared resources and hardware accelerators. So it's going to be a fun time. So what we need is a monitoring system that's independent of what's executing in the SoC. So I'd like to take just a few minutes to step back and describe a generic monitoring system. So a typical SoC, not too dissimilar to what you have. You have a bunch of processing cores, some DSPs, hardware accelerators, memory controllers hanging off some sort of interconnect. Mentor Analytics, Embedded Analytics, provides 4 classes of IP that may be useful in your case. Well, actually 3 of them will be useful for your application. The first set is a portfolio of analytics modules. The one on the left, for example, is a bus monitor. It's a protocol-aware and transaction-aware monitor. This means at runtime you can configure these monitors to look for certain transactions from certain masters, provide metrics such as bandwidth, latency, how long certain transactions take. You can do min-max average. You can also capture trace. The monitor on the right-hand side, the status monitor, this is a more generic logic analyzer type thing, but it has similar capabilities like counting, metrics generation, and trace capture. And then in the middle, we have something called a static instrumentation module, which allows for understanding how program flow in your cores is taking place because the code is statically instrumented, and also you can use that for hardware accelerators to do posted writes to that module. The data that these modules generate will go to a message passing fabric so that any data is transported using that and not the target system's interconnect, so we do not affect the target system's behavior in any way. The message fabric is also used for cross-triggering, so a particular module could say, I found something interesting, you now need to look at your bit, and so the same fabric is used, and which modules cross-trigger which other modules can be done at runtime. Typically, the data then ends up at one or more of the modules in our third class, which are communicators. In your application, Peter, you'll be using the Axi Communicator, which allows one of your cores to be able to control the embedded analytics modules and collect data from those. And then our fourth class of IP modules, and these are typically for high integrity and safety critical systems where they will affect the behavior of the system. And then finally, we have a way of locking down the system so we don't have access to certain parts of your chip. So your block diagram that you had, if we take that and augment that with some of the modules that you have, I think they look like this in the lovely orangey brown color. That's correct, isn't it, Peter? You have those modules in your system.
Those are exactly what we've got, yes.
So just to remind you what you have, that we have the Axi Communicator. This will allow one or more of the RISC-V cores to access and configure the modules at runtime and collect data that these modules generate and make some decisions on the behavior of the system. We have Axi bus monitors. These are runtime configurable and transaction aware. These will help with understanding the transactions going into and out of your NOC. Status monitor allows you to understand the behavior of things like the hardware accelerators and the GPIOs and your front end. And then finally, we have the static instrumentation block, and this will help with understanding program flow and a flow of operations that your hardware accelerators do. So let's look at a couple of examples. So if we take that bus monitor on the left, at runtime, you'll be able to configure that and do things like count the number of outstanding transactions coming out of your iCache or any other cache for that matter, and you can work out whether the branch predictor is predicting well or not, and if it isn't, you can get your system software guys to provide better hints. But because your timing budget is so tight, I think things like the duration of cache misses are important, and in fact the maximum duration is what's going to impact most. And then access to shared resources like SRAM, where you have lots of computational engines accessing that SRAM. If we have the bus monitor providing us with min-max average from within the module itself in a window of time, and you move on to the next window, that min-max average is sent to the analytics CPU. And from that, you can determine how much bandwidth is going to that shared resource. And as you can see in that rectangular box, all four CPUs access that shared RAM. And in this case, you're pushing the limits of the bandwidth that SRAM can support. We can take advantage of the fact that at compile time in the wireless world, you know how long tasks should take and what order those tasks should be. And that compile time can be compile time information can be passed to the analytics CPU, and then in combination with the data that the statically instrumented code and the hardware accelerators, the data that they send to the static implementation block, we can work out how the program flow and the baseband is actually operating in real time compared to what was the ideal program and timing flow. So with that information in mind, the ideal flow may look something like this. So you do the task scheduling and the flow should be like this. But in fact, what you find is because of the timing constraints, and sometimes you go past the slot boundary, the program flow may take this flow through the code, and that would mean that the analyzer CPU could detect that and alert the system CPU. To just describe it in a slightly different way, going back to Peter's timing diagram, the little round blobs could be the start and end of tasks and hardware accelerator activity. And from that, we can determine when a particular task starts and when a particular task ends. We can compare that with the compile time vectors that are inside the analytics CPU. And we can determine that actually this channel estimator is now taking longer, and so there's an overrun in this channel estimator, which will result in the PUCCH will fail to complete in time, and then you will have a failure with this slot overrun. And because we have the information from the bus monitors and the status monitors from other parts of the SoC, we can, this data would also be going to the analytics CPU in real time. And the analyzer CPU can then determine what caused this slot overrun to take place. And this is going to be very important in the field as you evolve your baseband software to track the evolving standards and also the upgrades that your operators will be putting in place. So in summary.
Yes. Well, thank you, Gaj. That's been a very good overview, and I can say we're actually already making use of a lot of these features in our device in emulation. So what we've seen here in this presentation is that 5G radio access networks are incredibly complex. There are hundreds of users in each base station, feeding lots of different radio units, lots of different antennas, and there are many network operators using software running on the same hardware, many of them with their own software. And standards are evolving at an increasingly fast rate, and people wanting to just add more features all the time. So what we've seen is that we need to be able to monitor non-intrusively what's going on inside a device in order to detect when any problems occur. We need to do this in the lab, in field trials where hopefully we'll iron out a lot of problems, but we also need to do it over the lifetime deployments in the field. And thanks to the IP that Mentor Embedded Analytics have provided, we do have a means of doing this. So thank you very much.
Thank you.